watching. Congratulations on reaching this module of our course, Introduction to OKE and Working with Managed Nodes. In this module, we'll take a look at the fundamentals of OKE and dive into working with managed nodes. You will learn the difference between basic and enhanced cluster configurations. We will take a look at serverless Kubernetes with virtual nodes. We will also cover supported images and shapes for worker nodes. We will then look at the prerequisites for cluster creation, which includes policy configurations, console workflows, and network resource configurations. Through hands-on demonstrations, you will gain practical experience in cluster creation using the quick and custom workflows. So let's get started. Welcome to the world of Container Engine for Kubernetes, often referred to as OKE. I am Mahendra Mehra and I am a senior OCI instructor at Oracle University. In this course, we'll take you on a journey to explore the ins and outs of this remarkable service. So what exactly is OKE? Well, Oracle Cloud Infrastructure Container Engine for Kubernetes is a fully managed, scalable, and highly available service that empowers you to effortlessly deploy your containerized applications to the cloud. But that's just the beginning. Let's dive deeper and explore how OKE can transform the way you and your development team build, deploy, and manage cloud-native applications. One of the defining features of OKE is the flexibility it offers. You can specify whether you want to run your applications on virtual nodes or opt for managed nodes. Regardless of your choice, Container Engine for Kubernetes will efficiently provision them within your existing OCI tenancy on Oracle Cloud Infrastructure. Creating OKE cluster is a breeze, and you have a couple of fantastic tools at your disposal: the console and the REST API. These make it super easy to get started. Let's go to the core of it. OKE relies on Kubernetes, which is an open source system that simplifies the deployment, scaling, and management of containerized applications across clusters of hosts. Kubernetes is an incredible system that groups containers into logical units known as pods. And these pods make managing and discovering your applications very simple. Not to mention, Container Engine for Kubernetes uses Kubernetes versions that are certified as conformant by the Cloud Native Computing Foundation, also abbreviated as CNCF. And here's the icing on the cake. Container Engine for Kubernetes is ISO compliant. We adhere to ISO IEC standards 27001, 27017, and 27018. That's your guarantee of a secure and reliable platform. Now, how do you access all this power? You can define and create your Kubernetes cluster using the intuitive console and the robust REST API. Once your clusters are up and running, you can manage them using the Kubernetes command line, also known as kubectl, the user-friendly Kubernetes dashboard, and the powerful Kubernetes API. Now let's talk about the magic behind the scenes. All the master nodes or control plane nodes are managed by Oracle. This includes components like etcd, the API server, and the controller manager, among others. To ensure reliability, we make sure multiple copies of these master components are distributed across different availability domains. And we don't stop there. We also manage the Kubernetes dashboard and even handle the self-healing mechanism of both the cluster and the worker nodes. All of these are meticulously created and managed within your Oracle tenancy. But at your end, you have the power to manage your worker nodes. Using different compute shapes, you can create and control them in your own user tenancy. So as you can see, it's a perfect blend of Oracle's expertise and your control. Let's talk about why OKE is your go-to solution for all things Kubernetes. Imagine a world where building and maintaining Kubernetes environments, be it master nodes or worker nodes, is no longer complex, costly, or even time consuming. OKE is here to make your life easier by seamlessly integrating Kubernetes with various container lifecycle management products, which includes container registries, CI/CD frameworks, networking solutions, storage options, and top-notch security features. And speaking of security, OKE gives you the tools you need to manage and control team access to production clusters, ensuring granular access to Kubernetes cluster in a straightforward process. In a nutshell, OKE offers a wealth of benefits. It empowers developers to deploy containers quickly, provides DevOps teams with visibility and control for seamless Kubernetes management, and brings together Kubernetes container orchestration with Oracle's advanced cloud infrastructure. This results in robust control, top tier security, IAM, and consistent performance. In conclusion, in this lesson, we covered the basics of OKE. We started by understanding what OKE is and explored its foundations built on Kubernetes. We've also discovered the key advantages it provides. I trust you found this lesson insightful. Join us in the next one, and thank you for watching. Hello and welcome to this lesson on basic clusters and enhanced clusters overview. In accordance with the ongoing enhancements to the OKE service, when creating a new cluster with Container Engine for Kubernetes, you specify the cluster type as one of the following. The first type is the basic clusters. Basic clusters support all the core functionality provided by Kubernetes and Container Engine for Kubernetes. Basic clusters come with a service level objective but not a financially backed service level agreement. This means that Oracle guarantees a certain level of availability for the basic cluster, but there is no monetary compensation if that level is not met. On the other hand, we have the enhanced clusters. Enhanced clusters support all available features, including features not supported by basic clusters. So let's go ahead and take a look at features supported by enhanced clusters. As we move towards a more digitized world, the demand for infrastructure continues to rise. However, with virtual nodes, managing the infrastructure of your cluster becomes much simpler. The burden of manually scaling, upgrading, or troubleshooting worker nodes is removed, giving you more time to focus on your applications rather than the underlying infrastructure. Virtual nodes provide a great solution for managing large clusters with a high number of nodes that require frequent updates or scaling. With this feature, you can easily simplify the management of your cluster and focus on what really matters, that is your applications. Managing cluster add-ons can be a daunting task, but with enhanced clusters, you can now deploy and configure them in a more granular way. This means that you can manage both essential add-ons like Core DNS and Kube Proxy, as well as a growing portfolio of optional add-ons like the Kubernetes dashboard. With enhanced clusters, you have complete control over the add-ons you install or disable, the ability to select specific add-on versions, and the option to opt in or opt out of automatic updates by Oracle. You can also manage add-on specific customizations to tailor your cluster to meet the needs of your application. Oracle manages the lifecycle of add-ons so that you don't have to worry about deploying them yourself. This level of control over add-ons gives you the flexibility to customize your cluster to meet the unique needs of your applications, making managing your cluster a breeze. Scaling your clusters to meet the demands of your workload can be a challenging task. However, with enhanced clusters, you can now provision more worker nodes in a single cluster, allowing you to deploy larger workloads on the same cluster, which can lead to better resource utilization and lower operational overhead. Having fewer, larger environments to secure, monitor, upgrade, and manage is generally more efficient and can help you save on cost. Remember, there are limits to the number of worker nodes supported on an enhanced cluster, so you should review the container engine for Kubernetes limits documentation and consider the additional considerations when defining enhanced clusters with large number of managed nodes. Ensuring the security of your cluster is of utmost importance in today's digital landscape. With enhanced clusters, you can now strengthen cluster security through the use of workload identity. Workload identity enables you to define OCI IAM policies that authorize specific pods to make OCI API calls and access OCI resources. By scoping the policies to Kubernetes service account associated with application pods, you can now allow the applications running inside those pods to directly access the API based on the permissions provided by the policies. Additionally, OCI Audit automatically tracks all API calls made by Kubernetes workloads running on the cluster, providing an extra layer of security and accountability. Ensuring high availability and uptime of your Kubernetes API server is essential for the smooth operation of your cluster. With enhanced clusters, you can now rely on a financially backed service level agreement tied to Kubernetes API server uptime and availability. This means that you can expect a certain level of uptime and availability for your Kubernetes API server, and if it degrades below the stated SLA, you will receive compensation. This provides an extra level of assurance and helps ensure that your cluster is highly available and performant. Now let's take a look at the notable features that are not supported by these clusters. So talking about the basic clusters, notable features which are not supported by basic clusters are the virtual node pools, fine-grained cluster add-on deployment and configuration, workload identity for enhanced security, increased numbers of worker nodes, and again financially backed service level agreement. So these are not supported by basic clusters. On the other hand, enhanced clusters support all features supported by basic clusters plus the ones that we saw in the previous slide. Let me talk about a few points to remember while creating basic and enhanced clusters. When using the console to create a cluster, a new cluster is created as an enhanced cluster by default, unless you explicitly choose to create a basic cluster. If you don't select any enhanced features during cluster creation, you have the option to create the new cluster as a basic cluster. When using CLI or API to create a cluster, you can specify whether to create a basic cluster or an enhanced cluster. If you don't explicitly specify the type of cluster to create, a new cluster is created as a basic cluster by default. Creating a new cluster as an enhanced cluster enables you to easily add enhanced features later, even if you didn't select any enhanced features initially. If you do choose to create a new cluster as a basic cluster, you can still choose to upgrade the basic cluster to an enhanced cluster later on. However, you cannot downgrade an enhanced cluster to a basic cluster. These points are really important while you consider selection of a basic cluster or an enhanced cluster for your usage. To wrap up, we learned about two types of cluster in OCI OKE, basic and enhanced. Enhanced clusters come with additional features and a financially backed SLA, while basic clusters provide core functionality without the added features. When creating a cluster, you have the option to choose between these two types. I hope you found this lesson interesting. See you in the next one. Thanks for watching. Hello and welcome to this lesson on serverless Kubernetes with virtual nodes. I am Mahendra Mehra and I am a senior training lead and evangelist with Oracle University. So let's get started. Mo, the solution architect, asked Trisha, who's the team lead, about the pharmacy application running on the OCI OKE cluster. Trisha responds positively and mentions that they haven't had any issue so far. However, she also admits that managing the nodes on the cluster requires some manual work and specific expertise which their team may not possess. Mo then suggests using virtual nodes, a feature offered on OKE, which Trisha hasn't heard of before. This feature can eliminate the need for manual work and reduce the need for specific expertise, making node management more efficient and cost effective. Trisha expresses her interest and asks Mo to explain more about virtual nodes. So, before we dive deep into virtual nodes, let's have a basic understanding of what managed nodes are. Managed nodes run on compute instances within your tenancy and are at least partly managed by you. In the context of Kubernetes, a node is a compute host that can be either a virtual machine or a bare metal host. As you are responsible for managing managed nodes, you have the flexibility to configure them to meet your specific requirements. You are responsible for upgrading Kubernetes on managed nodes and for managing cluster capacity. Nodes are responsible for running a collection of pods or containers, and they are comprised of two system components. The two most important components are the kubelet, which is the host brain, and the container runtime, such as CRI-O or containerd. Nodes have unique requirements that are specific to your workloads, such as GPUs, local NVMe drives, RDMA use cases, ARM or x86 architectures, and various other scheduling requirements. By targeting your workloads to specific nodes based on your requirements, you can optimize performance and resource utilization for your specific use cases. So now that we have an understanding of how managed nodes operate, let's go ahead and understand the virtual nodes. Virtual nodes, on the other hand, are fully managed and highly available nodes that look and act like real nodes to Kubernetes. They are built using the open source CNCF Virtual Kubelet project, which provides the translation layer between OCI and Kubernetes. Also note, OCI is the first major cloud provider to offer a fully managed virtual kubelet product that provides a serverless Kubernetes experience through virtual nodes. Virtual nodes are configured by customers and are located within a single availability and fault domain within OCI. Virtual nodes have two main components: pod management and container instance management. Virtual nodes delegates all the responsibility of managing the lifecycle of pods to virtual kubelet, while on a managed node, the kubelet is responsible for managing all the lifecycle state. A key distinction of virtual nodes is that they support up to 1,000 pods per virtual node, with the expectation of supporting more in the future. We will go over this in greater detail in the following lessons. So let's do a quick overview of the virtual nodes. Virtual nodes offer a fully managed experience where customers don't have to worry about managing the underlying infrastructure of their containerized applications. Virtual nodes simplify scaling patterns for customers. Customers can scale their containerized application up or down quickly without worrying about the underlying infrastructure, and they can focus solely on their applications. With virtual nodes, customers only pay for the resources that their containerized application use. This allows customers to optimize their costs and ensures that they are not paying for any unused resources. Virtual nodes can support over 10 times the number of pods that a normal node can. This means that customer can run more containerized applications on virtual nodes, which reduces operational burden and makes it easier to scale applications. Customers can leverage container instances, a serverless offering from OCI, to take advantage of many OCI functionalities natively. These functionalities include strong isolation and ultimate elasticity with respect to compute capacity. To wrap up, virtual nodes on OCI OKE offer a serverless Kubernetes experience, allowing customers to focus solely on their containerized application without worrying about managing the underlying infrastructure. I hope you found this lesson useful. See you in the next one. Thank you so much for watching. Hello and welcome to this lesson on supported images and shapes for worker nodes. Let's get started. When creating a cluster using Container Engine for Kubernetes, you have the flexibility to customize the worker nodes within the cluster. Now, this customization includes specifying two key elements. Firstly, you can select the operating system image to be used for worker nodes. This image serves as a template for the worker node's virtual hard drive and determines the operating system and other software installed. Secondly, you can choose the shape for your worker nodes. The shape defines the number of CPUs and the amount of memory allocated to each instance, ensuring it meets your specific requirements. This customization empowers you to tailor your OKE cluster to your exact needs. It is important to note that you can define and create OKE clusters using both the console and the REST API. This level of control is especially valuable for your development team when building, deploying, and managing cloud native applications. You have the option to specify whether applications should run on virtual nodes or managed nodes, and Container Engine for Kubernetes efficiently provisions them on Oracle Cloud Infrastructure within your existing OCI tenancy. This flexibility ensures that you can adapt your OKE cluster to suit the specific requirements of your projects and workloads. Moving on to the topic of supported images for managed nodes. It's essential to understand that Container Engine for Kubernetes supports the provisioning of worker nodes, specifically managed nodes, using a selection of Oracle Linux images provided by OCI. Now, these images fall into three categories: platform images, OKE images, and custom images. Let's start with platform images. Platform images are supplied by Oracle and exclusively contain an Oracle Linux operating system. When a compute instance hosting a managed node boots up for the first time, Container Engine for Kubernetes downloads, installs, and configures all the required software. To explore the platform images currently supported by Container Engine for Kubernetes using the CLI, you can check the supported images in the Data Sources section of the response by entering the command given on the screen. Keep in mind that the platform image names may or may not include a CPU architecture reference and do not include OKE in their names. For example, as you can see on screen, we have two outputs, Oracle Linux 8.5 and Oracle Linux 7.9. Both of them do not specify the CPU architecture, as well as there is no mentioning of OKE in their names. Let's discuss OKE images. The OKE images provided by Oracle are designed on the foundations of platform images. These OKE images are optimized to serve as the base image for the managed nodes. They come pre-configured with all the necessary settings and required software, ensuring a seamless experience. When creating and updating clusters and node pools, you have the option to choose OKE images as the base image for managed nodes. This choice significantly reduces the time it takes to provision managed nodes at runtime compared to using platform images or custom images. In fact, the use of OKE images can cut managed node provisioning time by more than half when compared to platform images. To discover the OKE images currently supported by Container Engine for Kubernetes, you have two options. If you prefer using console, simply select OKE images as the image source in the Browse All Images window during the custom create workflow. We'll be taking a look at it during one of our demos. This will allow you to view the list of supported OKE images. Alternatively, if you're using the CLI, you can examine the supported images in the Data Sources section of the response by entering the following command as shown on the screen. OKE images name have a specific format, making them easily distinguishable. They typically follow the format platform image name -OKE Kubernetes version -OKE build number. For example, the platform image name here is Oracle Linux 8.7 Gen 2 GPU and the date -OKE hyphen the Kubernetes version, which is 1.25.4, hyphen the OKE build number, which is 549 in this case. You must ensure compatibility. If you specify a Kubernetes version when creating and updating node pools, the OKE image you select must have the same version number as the node pool. Custom images provide you with the flexibility to design your own worker node images that suit your specific requirements. These custom images can be based on both the supported platform image and OKE images. If you are using OKE images as the foundation for your custom images, remember that OKE images are specific to a particular Kubernetes version and CPU architecture. A custom image typically contains an Oracle Linux operating system, and it can incorporate additional customizations, configurations, and software that were in place when you created the image. When provisioning managed nodes within a node pool, you can choose to use your own custom image instead of one of the predefined Oracle Linux images. Note that Container Engine for Kubernetes only supports custom images that are based on one of the Oracle Linux images returned by the OCIR node pool options get command. Now, to provision managed nodes using a custom image, you need to work with the CLI or API and specify the OSID of the custom image when creating the node pool. For example, you can use the OCIR node-pool create command and specify the double-node-image-id parameter along with the OSID of your custom image. There are a few additional considerations when working with custom images. OKE installs Kubernetes on top of a custom image, and this process may lead to change in certain kernel configurations. Custom image also requires access to a YAM repository, which can be public or internal. And to ensure the best support and compatibility, it's advisable to create custom images based on the most up-to-date base image. It's crucial to choose the right shape for your managed nodes to ensure optimal performance and resource allocation. For managed nodes, we have several shapes that are supported, and these include flexible shapes, with the exception of flexible shape for bustable instances like VM standard E3 Flex. We have bare metal shapes, which encompass both standard shapes and GPU shapes. We have HPC shapes except in the RDMA networks. VM shapes, which includes standard shapes and GPU shapes along with dense IO shapes. However, there are some shapes that are not supported for managed nodes, and these include dedicated VM host shapes, micro VM shapes, HPC shapes on bare metal instances in RDMA networks, and flexible shapes designed for bustable instances such as VM standard E3 Flex. Virtual nodes provide flexibility in managing your Kubernetes cluster, and it's essential to choose the right shape that suits your specific requirements. For virtual nodes, we have specific shapes that are supported, and these include pod standard A1 Flex, pod standard E3 Flex, and pod standard E4 Flex. These supported shapes that we saw for virtual nodes offer various options to cater to your specific workload needs. However, please note that all other shapes are not supported for virtual nodes. It's important to make the right choice to ensure that your virtual nodes operate optimally. To check which shapes are supported by Container Engine for Kubernetes and are accessible in your tenancy, you can view the supported shapes including specific shape options for virtual nodes by executing the following command, that is OCIR node pool options get node pool options ID all. And of course, you need to look into the data shapes section of the response whenever you hit enter on this particular command. To wrap up, in this lesson, we covered the intricacies of managing worker nodes in OKE. We discussed customizing worker nodes, explored various image options, and outlined supported shapes for both managed and virtual nodes. I hope you found this lesson useful. Thank you so much for watching. Hello and welcome to this lesson on prerequisite to create an OKE cluster. I am Mahendra Mehra and I am a senior OCI instructor at Oracle University. So let's get started. In this lesson, we will cover the fundamental prerequisites necessary to create an OKE cluster. So let's begin by looking at what you will need. First and foremost, you must have access to an Oracle Cloud Infrastructure tenancy. It's crucial to ensure that you have sufficient quotas on resources, also known as service limits. You will need a dedicated compartment that's ready for deployment. Configuration of your network resources is a crucial step in the process. We'll also discuss the importance of understanding policies in managing your OKE clusters effectively. Lastly, we will explore the essential tools that will be at your disposal to access your OKE cluster. Throughout this lesson, we will delve into each of these aspects in detail. So let's get started. The first step to success is gaining access to an Oracle Cloud Infrastructure tenancy. A tenancy refers to your Oracle Cloud account. And here's the good news. OKE or Container Engine for Kubernetes is available in all Oracle Cloud Infrastructure regions. This means regardless of the region you are in, you are well positioned to make the most of OKE. Your tenancy serves as the foundation upon which your OKE journey is built. Let's now explore the next critical prerequisite. It's essential to have sufficient quotas on different types of resources. Let's explore these resource quotas in detail. Compute instance quota. This quota depends on the compute shape you choose. It's determined by the number of compute cores and the memory required for a specific shape. For instance, creating a Kubernetes cluster with managed nodes and managed node pools require at least one compute instance. However, for a highly available cluster in a region with 3 availability domains, you will need at least 3 compute instances, one in each domain. Block volume quota. If you plan to create Kubernetes persistent volumes, ensure there's enough block volume quota in each availability domain to fulfill the persistent volume claim. Make a note that these claims should request a minimum of 50 gigabytes. Load balancer quota. If you are considering creating a load balancer to distribute traffic between nodes running a service in your Kubernetes cluster, make sure there's sufficient load balancer quota available within the region. When creating clusters, sufficient VCN and subnet quota must be available in the region. Now, in our preparation checklist, we come to the need for a ready to deploy compartment within your tenancy. This compartment is where we'll house the essential network resources, including a virtual cloud network, subnets, internet gateways, route tables, and security list. If you haven't already set up this compartment, you will need to create it. It's important to note that these network resources can exist in the root compartment, but here's a best practice tip. If you anticipate multiple teams creating cluster, it's advisable to create a dedicated compartment for each team. This ensures organization and simplifies management. Now let's proceed to the next step of our preparation. The next vital aspect is configuring network resources within the compartment. These resources include components like virtual cloud networks, subnets, internet gateways, route tables, and security lists. These components must be set up correctly in each region where you plan to create and deploy clusters. The best practice here is to opt for regional subnets, making failover across availability domains easier to manage. When creating a new cluster, you can choose to have Container Engine for Kubernetes automatically create and configure these network resources for you, or you can specify existing network resources. If you go with the later option, these resources should already be correctly configured. Now that we understand the importance of configuring network resources, let's proceed to our next prerequisite. Let's talk about policies. To create and manage clusters effectively, you need to belong to one of the following groups. Firstly, the Tenancy Administrators Group. This group carries the necessary permission to oversee Container Engine for Kubernetes. Alternatively, you can be part of a group to which a policy grants the appropriate Container Engine for Kubernetes permissions, which we will cover further in the upcoming lessons. Remember, policies play a crucial role in granting and managing permissions, so ensure that you are part of the right group or have the appropriate policies in place. In order to perform various Kubernetes operations on a cluster, there are a few key points you must know. First and foremost, you need to have the Kubernetes command line tool, also known as kubectl, at your disposal. You can either use the installation included in the Cloud Shell or set up a local installation of kubectl. We'll explore accessing a cluster using kubectl later on. Additionally, you must configure your own kubeconfig file for the cluster, a crucial step which we will cover in the upcoming lesson. Remember, each user must set up their own kubeconfig file. You cannot access a cluster with a kubeconfig file configured by another user. Last but not the least, to effectively interact with the cluster, you must have the appropriate permissions in place. As I already mentioned, we will look into the access control and policies in the upcoming lessons. As we conclude this lesson, we covered the essential prerequisites for preparing to create an OKE cluster. In the following lessons, we'll explore each of these prerequisites in depth to ensure you are well equipped for the journey ahead. Thank you for watching, and I'll see you in the next lesson. Hello and welcome to this lesson on policy configuration for cluster creation and deployment. In this lesson, we will thoroughly examine the crucial policies, including both required and optional components that enable user groups to carry out various actions concerning OKE cluster operations. So let's get started. When a tenancy is created, an administrator group is automatically established. Members of this group have broad permissions to manage resources within the tenancy. Users who are part of the administrators group can execute various operations on resources without needing for additional policies. However, if you intend to grant permissions to users who are not part of the administrator group for using Container Engine for Kubernetes, you'll need to create specific policies. These policies empower user groups, enabling them to carry out actions on resources within the tenancy or individual compartments. The required and optional policies will be discussed in the upcoming slides. In addition, certain policies are essential for specific scenarios such as creating and utilizing clusters with virtual nodes and virtual node pools. Also, in scenarios such as encrypting data in boot volumes and block volumes with your own master encryption keys from the OCI Vault service. It's worth noting that the Kubernetes RBAC authorizer can also be used for enforcing fine-grained access control for users on particular cluster through Kubernetes RBAC roles and cluster roles. Moving on, to enable users to effectively use OKE for tasks like creating, updating, and deleting clusters as well as node pools, you need the following required policy statements. Policy statements such as allow group To manage instance family, policy statements such as allow group to use subnets, to read virtual network family, to use network security groups, even to use VNIX, as well as to inspect compartments and to use private IPs and manage public IPs. Right, so these are the policy statements that you need to put in place for you to work with OKE. And you must make sure that you replace group name with the name of the user group, as well as the location placeholder with either tenancy if you're creating the policy in the tenancy's root compartment, or you can replace the location with a compartment name if you're creating the policy in an individual compartment. To ensure comprehensive access to cluster related resources, we have a catch all policy, and this single policy statement grants groups the authority to manage cluster family resources within the given location. In essence, it empowers all users with administrator level privileges concerning any cluster related resources. Also note that the specific type of cluster you are working with may influence necessity of certain required policy statements. For VCN native clusters where the Kubernetes API endpoint is fully integrated within your VCN, the use of private IPs policy is always required. However, the use of public IP policy statement is only essential if you have selected the option for cluster to have a public IP address. Additionally, when dealing with clusters where the public Kubernetes API endpoint is in an Oracle managed tenancy, you won't need the use VNIX, use private IPs, and manage public IPs policy statements. To enable users in a group to automatically create and configure associated network resources when creating a new cluster in the quick create workflow, you must also grant policies to the group with the following permissions. You must allow the group to manage VCNs. The group must have permission to manage subnets, manage internet gateways, manage NAT gateways. The group must also have permissions to manage route tables as well as manage security list in the given location. As I already mentioned in the previous slide, the location can be your tenancy or it can be an individual compartment where you're trying to create these resources. And you must replace the group name placeholder with the appropriate group name. In addition to the required policies we discussed in the previous slides, there are also some optional policies that can further enhance your control over the OKE service. And these optional policies grant user specific permissions and access for various OKE related actions. Let's take a look at them. The first one is the Cloud Shell policy. To enable a user group to access clusters using Cloud Shell, you must enter a policy statement as shown on the screen, which allows user group to use Cloud Shell. The default location is tenancy. Let's look at the vault related policy. To enable a user group to select master encryption keys and vaults in the vault service when creating and modifying clusters using the console, you must grant them the read vaults as well as read keys permissions. You can also set up cluster related policies. For example, you can set up policies that allows group to inspect clusters in a given location, allowing group to use cluster node pools in a given location, allow group to read cluster work requests in a given location. We can also set up service gateway related policy that allows the group to manage service gateways in a given location. Now, this particular policy would allow a group to create a service gateway to enable worker nodes to access other resources within the same region without exposing the data to public internet. You can also set up policies for capacity reservation, where you can reserve compute capacity for clusters you've created using Container Engine for Kubernetes. To enable users in a group to use capacity reservation, you must grant them the permission to use compute capacity reservation in a given location, which could be tenancy or a particular compartment. With this, we come to the end of this lesson where we've covered the essential policies you need to configure for creating and deploying clusters in OKE. We discussed both the required policies, which are necessary for basic functionality, and optional policies that provide additional control and security. So thank you for joining us, and I will see you in the next lesson. Hello and welcome to this lesson on creating Kubernetes clusters using console workflows. In this lesson, we will explore different ways to create an OKE cluster. So let's get started. Whether you are a member of the tenancies administrator group or have been granted the necessary permissions through policies, we'll walk you through the steps to configure your cluster. You will have the choice between the quick create workflow with default settings and the custom create workflow, which allows for more personalized configurations. Let's understand the quick create workflow, an expedited method for creating a new Kubernetes cluster in Oracle Kubernetes Engine. This approach is designed for swift deployment, allowing you to utilize default settings to get your cluster up and running with just a few clicks. One of the advantages of Quick Create is its automatic creation of necessary network resources, including regional subnets for Kubernetes API endpoint, worker nodes, and load balancers. The load balancer's regional subnet is public, while you can specify whether the regional subnets for Kubernetes API endpoint and worker nodes are public or private. Please note that to create a cluster using the Quick Create workflow, you need to belong to a group that's been granted the necessary permissions through policies. Let's understand Custom Create workflow, which provides you with maximum control over the creation of your new Kubernetes cluster. With custom settings, you can tailor your cluster properties, including encryption, exactly to your preferences. Additionally, you have the precision to specify existing network resources for your cluster, choosing between public or private subnets for the Kubernetes API endpoint, worker nodes, and load balancers. But what makes the custom create workflow truly unique is the flexibility it offers. You can define node pools immediately when creating the cluster, or you have the option to delay this step. In fact, you can even start with a cluster that has no node pools and then add them later on. Creating a node pool free cluster can be particularly advantageous, especially if you plan to install Calico or a network policy provider for Kubernetes. It's advisable to create a cluster initially without node pools. This avoids the need to recreate pods once the installation is complete. Installing Calico before creating node pools is a recommended best practice for a smoother and more efficient deployment. Besides using quick create and custom create workflow in the console, you can create clusters via the CLI and API. Let's navigate to the official documentation, and here you will find comprehensive information about CLI and API options for managing your OCI resources, including OKE cluster. Here, as you can see, we have three options: console, CLI, and API. When I click on the CLI tab, it outlines the command line interface options for configuring and managing your OKE resources. And when I click on the API tab, you can use the create cluster operations to create a cluster. So when I click on this link over here, this page details information on how to use the create cluster operation using several SDKs like Java, Python, and many more, as you can see on the screen. You can also use OCI Resource Manager Stack or Oracle Terraform modules to set up a Kubernetes cluster in your OCI tenancy. Here on our GitHub page, you will find Terraform modules that makes setting up an OKE cluster a breeze. You can easily configure your cluster with the help of these modules, saving time and effort. To wrap up, in this lesson, we explored the various methods for creating OKE clusters, from the quick and easy quick create workflow to the highly customizable custom create approach. You also learned that the cluster creation can be achieved through the CLI and API for more advanced users. We also saw that you can use the OCI OKE Terraform modules to spin up cluster with ease using Terraform modules or Resource Manager Stack. With these options at your disposal, you have the flexibility to create OKE cluster that best suits your need. Thank you for watching, and I'll see you in the next lesson. Hello and welcome to this lesson on network resource configuration for custom cluster creation and deployment. So let's get started. In this lesson, we will explore the key network resources required for configuring a custom OKE setup, such as VCN configuration, subnet configuration, internet gateway configuration, NAT gateway configuration, service gateway configuration, route table configuration, DHCP option configuration, and security rule configuration in network security group and or security list. These resources are vital for the smooth deployment of your clusters. First up, let's take a look at VCN configuration. VCN configuration is the bedrock of your custom OKE cluster, and it's crucial to get it right. Here are some compelling reasons why VCN configuration deserves your utmost attention. Your VCN must have a properly defined CIDR block that's spacious enough to accommodate all the critical cluster resources. This includes the Kubernetes API endpoint, worker nodes, pods, and load balancers. A /16 CIDR block like 10.0.0.0/16, for example, is generally sufficient for most use cases. An adequate number of subnets must be set up for various purposes, such as worker nodes, load balancers, the Kubernetes API endpoints, and pods. Using regional subnets is considered best practice as it simplifies failover across availability domains. To protect your cluster and network, it's essential to define security rules. These rules can be configured in network security group or security list for each subnet. Selecting DNS resolution for VCN ensures that your cluster can efficiently resolve DNS names, an essential aspect of networking. The choice between public and private subnets determines whether your VCN should have an internet gateway, NAT gateway, or both. These components enable network connectivity and data transfer. A well-structured route table is crucial if your VCN is equipped with gateways. It directs network traffic effectively, ensuring that data reaches its destination as intended. Next, we will take a look at subnet configuration. Subnet configuration, a vital aspect of your custom OKE setup. The specifics of your cluster and your deployment needs will determine how many subnets you need to configure. In line with best practices, using regional subnets simplifies failover across availability domains. In the VCN where you intend to create and deploy your clusters, it's essential to have at least two different subnets, including a subnet for Kubernetes API endpoint, a subnet for worker nodes, optionally one or two load balancer subnets, which could be regional or availability domain specific, a subnet for pods, and optionally a bastion subnet. Remember that your subnet CIDR blocks should not overlap with the CIDR blocks specified for pods within the cluster. Please note that configuring worker node subnets and pod subnets may vary when using virtual nodes instead of managed nodes, as each has distinct requirements for proper functioning. Internet gateway configuration. This is essential when your custom OKE cluster involves public subnets that require internet access. Let's break down why this is crucial. First, if you plan to use public subnets for components like worker nodes, load balancers, or Kubernetes API endpoints, you must have an internet gateway. Public subnets are designed to interact with the internet, but the gateway is the key that makes this possible. The Internet Gateway serves as the entry and exit point for data traveling to and from the Internet. To make this work seamlessly, you need to specify the Internet Gateway as the target for the destination CIDR block 0.0.0/0 within your route table. NAT gateway configuration. This is also a key element for custom OKE clusters that utilize private subnets. Here's why NAT gateway is crucial. When you are planning to deploy components like worker nodes, the Kubernetes API endpoints, or pods in private subnets, you might still need internet access for various reasons. Private subnets offer enhanced security, but they lack direct access to internet. A NAT gateway bridges this gap. To enable private subnets to access the internet securely, a NAT gateway must be in place. It acts as an intermediary, allowing your resources within private subnets to initiate outbound connections to the internet. To make this work effectively, you need to specify the NAT gateway as the target for the destination CIDR block 0.0.0/0 in one of your route tables. Service gateway configuration plays a vital role in your custom OKE cluster setup, and here's what you need to know. If you're planning to use private subnets for worker nodes, the Kubernetes API endpoints, or pods, especially when employing the OCI VCN native pod networking CNI plugin, having a service gateway in your VCN is a must. I'm sure you must be wondering what's OCI VCN native pod networking CNI plugin. We will be discussing these pod networking plugins in the upcoming lessons. To set up a service gateway, ensure it is created in the same VCN compartment as the subnet for your worker nodes, the Kubernetes API endpoints, or the pods. While configuring it, select the All Region Services in Oracle Service Network option, as it enables your subnets to access the essential Oracle Services network. To complete the setup, specify the service gateway as the target for all region services in Oracle Services Network as a route rule in one of your route tables. When setting up your custom OKE cluster, you will need to configure route tables for various subnets. Let's break it down. For worker node subnets, especially the public subnet, you'll need a route rule directing traffic to the internet gateway as target for the destination CIDR block 0.0.0.0/0. And for private subnets, configure a route rule targeting the service gateway for all region services in Oracle Service Network and another one for the NAT gateway as the target for the destination CIDR block, again 0.0.0.0/0. The route rule remains same for the Kubernetes API endpoint subnets for public as well as private subnets. For load balancer subnets, just like the worker nodes, create a route rule targeting the internet gateway for 0.0.0.0/0. For private subnet, in this case, you can leave the subnet route table empty. Lastly, talking about route table rules for pod subnet. For the pod subnets, basically when using the OCI VCN native pod networking CNI plugin for pod networking, pods go in a private subnet. So you don't have to configure anything for the public subnet. You must configure the service gateway as target for all region services in Oracle Service Network and the NAT gateway as the target for destination CIDR block 0.0.0.0/0. These configurations ensure proper routing within your custom OKE cluster. Now let's discuss DHCP options configuration. Again, this is crucial for your VCN. So for your VCN where you plan to create and deploy clusters, you need to make sure that the DHCP options are correctly configured. Fortunately, the default settings for DNS type, which is Internet and VCN Resolver, is perfectly suitable. This ensures that your VCN's domain name system is in a good shape. Security rule configuration in network security group and or security list. The VCN where you are planning to create and deploy your cluster should have a well-defined security rules. These rules can be specified in two ways. First, in the network security groups, which is the recommended approach. These groups are selected for node pools, the Kubernetes API endpoints, pods, particularly when using the VCN native pod networking, and load balancers if applicable. All of these when creating a cluster. Second, you can define security rules in security lists that are already associated with the subnets designated for worker nodes, Kubernetes API endpoint, pods, and load balancers. One essential point to note: if you choose to specify security rules in both network security group and security list, all these security rules are applied, essentially forming the union of the security rules. Keep in mind that the worker nodes, the Kubernetes API endpoint, pods, and load balancers have distinct security rule requirements. If necessary, you can add extra rules to cater to your specific needs. Within the realm of security, OKE demands a comprehensive set of rules to ensure the safety and integrity of your clusters. Due to the extensive nature of these rules, we have made it simple for you. Rather than overwhelming you with an exhaustive list of security rules here in this slide deck, we've made it convenient for you to access the latest and the most detailed information directly from the official Oracle documentation. Let's switch to the browser and let me quickly show you the official documentation where you have access to all the security list and the rules. So this is the official documentation, and within the container engine you can search for preparing for container engine for Kubernetes, and there's this page on network resource configuration for cluster creation and deployment. On this page, when you scroll down, you will find a comprehensive breakdown of the specific security rules that are required to configure various aspects of your OKE environment, including security rules for Kubernetes API endpoints, which includes both ingress and egress rules, security rules for worker nodes, security rules for pod subnets. You must also specify security rules for bastion subnets based on your use case. And that concludes our exploration of network resource configuration for custom cluster creation and deployment. We've ventured into the essential components of setting up a custom OKE cluster, covering everything from VCN and subnet configuration to DHCP options and security rules. By now, you should have a solid understanding of the intricate details required to create a cluster that suits your unique needs. Thank you for joining us in this lesson, and I look forward to seeing you in the next one. Hello and welcome to this lesson on understanding networking connectivity for pods running on worker nodes. In Kubernetes, pods rely on unique and routable IP addresses to communicate with each other, with the cluster's control plane node, with pods on other clusters, and with other services such as storage service, and sometimes with the broader internet. Let's explore this vital networking model in this lesson. Let's begin our exploration of the Container Network Interface, also known as CNI specification, a pivotal framework in the world of Kubernetes and network resource management. CNI is a versatile framework that encompasses a specification and libraries, allowing for the creation of various plugins designed for Linux container network setup. These plugins come in a variety of flavors tailored to meet diverse network configuration requirements. Now let's delve into the crucial role that CNI plugins play with Kubernetes cluster. CNI plugins streamline the setup of network interfaces for pods running on worker nodes. They are responsible for the assignment of IP addresses and the maintenance of network connections. Depending on the specific network type you choose, Kubernetes utilizes different CNI plugins to facilitate these processes. When it comes to network types, your choice has a direct impact on the CNI plugin you'll be working with. For instance, if you opt for VCN native pod networking, it aligns with the OCI VCN native pod networking CNI plugin. On the other hand, if you are using the Flannel overlay network type, you will be working in tandem with the Flannel CNI plugin. It is important to recognize that consistency matters when it comes to CNI plugins in Kubernetes cluster. All node pools within a single cluster must utilize the same CNI plugin. When creating a cluster, your choice of the CNI plugin is definitive and it cannot be modified later. So it's a decision that carries weight. Now let's address the management of CNI plugins versions within your cluster. When a cluster is initiated, it initially employs the most recent version of the CNI plugin. You have the flexibility to decide whether you'd like Oracle to manage updates automatically or if you prefer to select versions manually. If you opt for manual updates, you are committing to keeping the CNI plugin add-on up to date and aligned with your cluster's needs. In the realm of Kubernetes, the CNI plugin for pod networking emerges as an essential cluster add-on. Your choice of network type directly determines which version of the CNI plugin is in use. This choice will significantly impact how your clusters operates, so it's a decision worth careful consideration. Let's take a close look at Flannel CNI plugin for pod networking. One of its standout features is that it allows pod networking without utilizing IP addresses from the VCN's CIDR block. This decoupling ensures more efficient resource allocation. The magic happens within the Flannel overlay network, a simple yet powerful private overlay virtual network. It adheres perfectly to the requirements of the Kubernetes networking model by attaching IP addresses to containers. This means that pods can communicate with each other, promoting security and isolation, and access is confined to pods within the same cluster. But one thing to note is you can use the Flannel CNI plugin with managed node pools, but not with virtual node pools. Let's understand the Flannel CNI plugin for pod networking with the help of this diagram. When creating a cluster with Container Engine for Kubernetes and using the Flannel CNI plugin for pod networking, you specify CIDR blocks for the Kubernetes service, as well as CIDR blocks that can be allocated to pods running in the cluster. Now, there are a few things that you must note when using Flannel CNI plugin for pod networking. The Kubernetes API endpoint subnet only requires a small CIDR block, since the cluster only requires one IP address in this subnet. So basically, a /30 CIDR block of network address is sufficient for the Kubernetes API endpoint subnet. The CIDR blocks you specify for pods running in the cluster must not overlap with the CIDR blocks you specify for the Kubernetes API endpoint, worker node, and load balancer subnets. Each pod running in the worker node is assigned its own network address. Container Engine for Kubernetes allocates a /25 CIDR block of network addresses for each worker node in a cluster to assign to pods running on that worker node. A /25 CIDR block equates to 128 distinct IP addresses, of which one is reserved. So a maximum of 127 network addresses are available to assign to pods running on each worker nodes, which is more than sufficient given that the number of pods per node is capped at 110. When you create a cluster, you specify a value for the cluster's pod CIDR block property, either implicitly in the case of quick create workflow or explicitly in the case of the custom create workflow. Now the catch here is you cannot change the cluster's pod CIDR block property after the cluster has been created. The cluster's pod CIDR block property will actually constrain the maximum number of network addresses available for the allocation to pods within each of these nodes, and therefore effectively limits the number of nodes in the cluster. By default, the cluster's pod CIDR block property is set to /16 CIDR block, and specifying /16 as the CIDR block for the cluster's pod CIDR block property limits the number of nodes in the cluster to 512. This is generally sufficient, but to support more than 512 nodes in a cluster, You must create a cluster in the custom create workflow and specify a larger value for the cluster's pod cider block property. As this video is getting a bit lengthy, I'll pause here. We'll pick up right where we left off in the next video. So see you in the next video. Welcome back. If you missed the previous video, be sure to check it out for essential context. Now let's pick up where we left off. Let's explore the OCI VCN native pod networking CNI plugin and its role in optimizing pod networking. Here are the key points that you must know. Dual subnet configuration. Worker nodes are connected to two specified subnets for node pool configuration, creating a versatile network environment. Worker node subnet. This subnet facilitates communication between the processes on the cluster control plane, such as Kube API Server, Kube Controller Manager, or Kube Scheduler, and worker node processes such as Kubelet or Kube Proxy. It can be private or public with a regional subnet or different availability domain specific subnets as recommended options. Pod subnets. The pod subnet empowers pod-to-pod communication and direct access to individual pods using private pod IP addresses. It must be a regional subnet enabling communication within the same worker node across nodes with OCI services via service gateway and with internet through a NAT gateway. Let's understand the OCI VCN native pod networking CNI plugin with the help of this diagram. So when creating a cluster with container engine for Kubernetes and using the OCI VCN native pod networking CNI plugin, basically for pod networking, you specify the CIDR blocks for the Kubernetes service. Note, the CIDR block you specify for the VCN and subnets must not overlap with the CIDR block you specify for the Kubernetes service. The Kubernetes API endpoint subnet only requires a small CIDR block, since the cluster only requires one IP address in the subnet. So basically a /30 CIDR block is more than sufficient for the Kubernetes API endpoint subnet. Every worker node in the node pool has a primary virtual network interface card with a primary IP address. Depending on the shape you choose for the node pool, each worker node might have one or more secondary VNICs attached to it as well. The VNICs reside in the subnet selected for pod communication. Each VNIC can be associated with multiple secondary IP addresses. A pod running on a worker node can obtain a secondary IP address from a VNIC, assign the IP address to itself, and use the IP address for inbound and outbound communication. Every secondary VNIC attached to the worker node can assign up to 31 secondary IP addresses. And to calculate the maximum number of pods in a node pool of a particular shape, you can use the following equation. Let's take a look at some key considerations when using the OCI VCN native pod networking CNI plugin. You can use the OCI VCN native pod networking CNI plugin with both virtual node pools and managed node pools. You can only use the OCI VCN native pod networking CNI plugin with clusters running Kubernetes version 1.22 or later. If you are using the OCI VCN native pod networking CNI plugin and you want to specify an OKE image as the base image for the worker nodes, do not select an OKE image released before June 2022. Service mesh products such as Oracle Cloud Infrastructure Service Mesh, Istio, and Linkerd are supported when using the OCI VCN native pod networking CNI plugin, of course for pod networking. Note that the support is currently limited to Oracle Linux 7. We have Oracle Linux 8 support, which is planned, and worker nodes must be running Kubernetes 1.26 or later. When using the OCI VCN native pod networking CNI plugin, certain security rules are required for the pod subnets and the worker node subnets. To know more about the security rules that you must configure when using the OCI VCN native pod networking CNI plugin, you can refer the OCI official documentation, and here you get the complete information on the ingress rules and the egress rules that must be defined for pod subnets. Let's understand how to update the OCI VCN native pod networking CNI plugin. When you specify VCN native pod networking as a cluster's network type, the cluster and its node pools initially use the latest version of this plugin. Updates to the OCI VCN native pod networking CNI plugin are released periodically. You can specify that you want Oracle to deploy the updates on the cluster automatically, which is the default behavior. Alternatively, you can specify that you want to choose the version to deploy. If you decide to choose the version, you are taking responsibility for keeping the add-on up to date. Regardless of whether you or Oracle is responsible for deploying updates to this plugin, the updates are only applied when worker nodes are next rebooted. To determine whether updates have been deployed and are waiting to be applied, inspect the VCN native IP CNI daemon set logs by entering the following command. How to interpret the response to the command. If there is an output, it means updates to the plugin are pending and they'll be applied during the next worker node reboot. And if there are no output, no updates are waiting to be applied. With this, we come to the end of this lesson where we covered the Flannel CNI plugin for pod networking and also covered in depth the OCI VCN native pod networking CNI plugin. I hope you found this lesson useful. See you in the next one. Thank you for watching. Hello and welcome to this lesson on network resource configuration for cluster creation and deployment. In this lesson, we will cover some of the examples of how you might configure network resources when using the custom create workflow to create highly available clusters in a region with 3 availability domains. So let's take a look at our first example, which is cluster with Flannel CNI plugin having private Kubernetes API endpoints, private worker nodes, and public load balancers. As you can notice in the diagram, the Kubernetes API endpoint lies within the public subnet, the worker nodes lies in the private subnet, and the load balancer lies in the public subnet. So as you can notice from the diagram, the Kubernetes API endpoint and the load balancers are accessible directly from the internet, while the worker nodes remain within the VCN in a private subnet. Keep in mind the Kubernetes API endpoint defaults to a private IP address, but we can expose it to the internet by selecting a public subnet and specifying a public IP address. You can also notice a bastion host within the bastion subnet, which is hosted in a private subnet. Now, this is useful in cases where you wish to SSH into your worker nodes or Kubernetes API endpoints. The connectors going in and out of these subnets basically defines the ingress and egress rules that you must have for these subnets in order to have those The connectors moving in and out of these subnet blocks basically defines the ingress and egress rules that you must set up for these subnets in order to control communication to and from these blocks. As we delve into the specifics, feel free to refer to the official documentation for the detailed networking setup. So how do you access the official documentation is by reaching the docs.oracle.com site. And here you can simply click on Container Engine for Kubernetes. Also, you can search for Container Engine for Kubernetes in the search bar. So let me click on Container Engine for Kubernetes. So this brings you to the page where we have all the information regarding the Container Engine for Kubernetes. And this particular example that we are discussing is under the Preparing for Container Engine for Kubernetes section. So let me expand this and just click on Example Network Resource Configurations. So we are discussing example number 1. Similarly, we'll be discussing example 2, 3 and 4. So let's click on example number 1. Here you will find the detailed information about the networking setups, including the VCN subnets, route tables that you must configure, and security list rules for each of the subnets, including the ingress rules and the egress rules. For this example, you need a VCN resource, you need an internet gateway configured, you need a NAT gateway, a service gateway, and a DHCP option which is set to type internet and VCN resolver. You must also configure subnets. For example, for the Kubernetes API endpoint, we need a public subnet. For worker nodes, we need a private subnet. For load balancers, we need a public subnet. And again, for Bastion, we need a private subnet. Then we must configure route tables for each of these subnets, right? So for the public API endpoints, we must configure a route rule which has a destination slider block which is 0.0.0.0/0, and the target type is internet gateway. Similarly, for a private worker node subnet, we must configure two rules as we discussed in the previous lessons. One is rule for the traffic to internet and one is rule for traffic to OCI services. And again, for the public load balancer subnet, we need one route rule, that is to allow traffic to move to the internet using the internet gateway. And then these are the security list rules that you must configure for each of the subnets, including ingress rules. So I'm not going to read each of them. These are the de facto ingress rules and the egress rules that you must configure. Right. Similarly, you must configure security rules for your private worker node subnet, including the ingress and the egress rules, and security list for your public load balancer subnet, as well as security rules for private Bastion subnet. So let's go back to the slide for example number 2. So let's explore example number 2. In this setup also we are using the Flannel CNI plugin. However, in this case, only the load balancer is in the public subnet, which is accessible from the internet. Otherwise, we have the Kubernetes API endpoint and the worker nodes both being set up in a private subnet. And we do this basically to ensure added security and control so that your API endpoint and the worker nodes are not exposed to the internet. In any case, if you wish to access these resources, you can always do it using a Bastion host. The detailed setup for example number 2 is available in the official documentation. As you can see over here in example number 2, we have all the resources that you must configure to set up example number 2, including the VCN and other resources, subnets, as well as the route tables and the security list rules. Moving on to example number 3, here we are using the OCI VCN native pod networking CNI plugin. The highlight of this example is having a pod subnet. The Kubernetes API endpoint and the load balancers are set up in a public subnet, which means they are accessible from the internet, with worker nodes and the pod subnet being secured within the VCN in a private subnet. So as we discussed in the previous lessons, pod subnet helps you with pod communication and direct access through private pod IP addresses. If you wish to configure this setup while using the custom create workflow, you can always refer the official documentation and move to example number 3. So let me bring up the example number 3 over here. And you can basically configure all the resources as given in the detailed information regarding this example. So you can configure VCN, internet gateway, NAT gateway, service gateway. You can also set up subnets. So like we discussed, your API endpoint is in a public subnet, your worker nodes is in a private subnet. You have a separate subnet for pod, which is in a private subnet. And then you have public subnet for your load balancers and private subnet for Bastion. Similarly, you must configure route rules for your public and private subnets. And you must set up ingress and egress rules for each of these subnets, including the new private pod subnet. Lastly, in example number 4, we maintain the OCI VCN native pod networking CNI plugin. Only the load balancers are exposed to the internet, which means they are kept in a public subnet, whereas the Kubernetes API endpoint, the worker node subnet, and the pod communication subnet, they are all within the private subnets. And like I had already mentioned, you can also configure a Bastion host in order to access these resources within the private subnets. The connectors moving in and out of these resources basically represent the ingress and egress rule that you must configure for each of these subnets, which is already given in detail in the official documentation. So let me quickly show you the example number 4 in the official documentation and the various setup that you must configure. So if you scroll down, you get to see example number 4, which is cluster with OCI CNI plugin, having private Kubernetes API endpoint, private worker nodes, and public load balancer. And these are all the resources that you must configure, including the subnets and the route tables for each of these subnets, as well as the security list rules, including the ingress rules and the egress rules for each of the subnets. I'll be covering one of these examples in details while we set up a Kubernetes cluster using the custom create workflow. So with this, we come to the end of this lesson, and I just want to emphasize that the examples we saw are just the starting point for your configurations. For more detailed insights and a comprehensive understanding of setting up the required networking and security resources, I encourage you to refer the official documentation. Thank you for being here. Excited to have you back for our next lesson. See you there. Hello and welcome to this demo on create cluster using default settings in the quick create workflow using managed nodes. So let's get started. I've already logged in into my OCI account and this is my console. In the console, I'll first click on the navigation menu and then click on the developer services. Here under the container and artifacts section, let's click on Kubernetes cluster. On the left hand side from the list scope, you must select the compartment that you have the permission to work in. I'm running this demo as an administrator, so I have the privilege to work in the compartment that I've chosen. The compartment that I've chosen is CTD OKE. Now on the cluster list page, click on create cluster. In the cluster dialog box, we get two options, either to go for quick create or to go for custom create option. For this demo, I'll go with the default selection, which is quick create, and click on submit. And as you can notice, these are all the new resources that would get created when we create our cluster. So let me go ahead and click on submit. On the cluster create page, either just accept all the default configuration details for the new cluster, or we can specify alternatives. So let me go ahead and change the name here. Since I'll be configuring the managed nodes in a public subnet, let me give it a name public -demo-1. This is the exact compartment where I want to create this cluster. So let's go ahead. Under the Kubernetes version, you get to select the Kubernetes version you wish to run on the control plane nodes and the worker nodes of the cluster. So either accept the default version, which is currently version 1.27.2, or we can select a version of our choice from the list. I'll go with the default selection. The Kubernetes API endpoint section defines the type of access to the cluster's Kubernetes API endpoint. You can either select private endpoint or go for public endpoint. When you select private endpoint, a regional private subnet is created and the Kubernetes API endpoint is hosted in that subnet. So the Kubernetes API endpoint is assigned a private IP address. But if you go for a public endpoint, a public regional subnet is created and the Kubernetes API endpoint is hosted in that subnet. And of course, the Kubernetes API endpoint is assigned a public IP address as well as a private IP address. So let me go with the default selection, which is public endpoint. Under the node type section, you must specify the type of worker nodes in the first node pool in the cluster. Now you have two options, managed or virtual. I'll go with the managed node selection. And when I select the managed node option, basically it is my responsibility for managing the worker nodes in the node pool. We will talk about virtual nodes in the upcoming demos. So let me proceed. Under the Kubernetes worker nodes section, we specify the type of access to the cluster's worker nodes. The worker nodes are either private, only accessible via the VCN subnets, or public, accessible directly from the internet. And like I mentioned, for this cluster, I'll be placing them in a public subnet. So let me go ahead and select the public workers. Remember, when you select public workers, a public regional subnet is created to host our worker nodes, and the worker nodes are assigned public IP address as well as private IP address. If I would have gone for private workers, which is of course a recommended approach, a private regional subnet is created to host worker nodes, and the worker nodes are assigned private IP address. But we'll stick to public workers. Let's move on. Under the shape and image section, you can first select the node shape. This shape determines the number of CPUs and the amount of memory allocated to each node. If you select a flexible shape as shown on the screen, you have the flexibility to specify the number of CPUs and the memory for that shape. Also, when you click on the list, you get to see the list of supported shapes in your tenancy to run the worker nodes in your Kubernetes cluster. Let me proceed with the default selection. Moving on, under the image section, you get to choose the image to use on the worker nodes in the manage node pool. An image is a template of a virtual hard drive that determines the operating system and other softwares for the manage node pool. If you wish to change the default image, you can select on change image, and then you can browse through the list of images that you wish to include in your worker nodes. From the list, you can either choose an OKE worker node image, which is of course recommended since they are provided by Oracle and built on top of the platform images. These serves as the base image for your worker nodes with all the necessary configuration and the required software. Whereas if you go for the platform images, these are provided by Oracle and only contain an Oracle Linux operating system. So you should go for platform image if you want container engine for Kubernetes to download, install, and configure all the required software when the compute instance hosting your worker nodes boots up for the first time. So I'll go ahead with the default selection, that is the OKE worker node image, Oracle Linux 8. At the very bottom, we get to specify the node count. Node count here specifies the number of worker nodes to create in the node pool, which will be placed in the regional subnet created for the cluster. Now, remember, the nodes are distributed as evenly as possible across availability domain in a region, or in case of a region with single availability domain, across different fault domains in that availability domain. Now let's click on show advanced options. Under advanced option, you get an option to specify boot volume, image verification, and add an SSH key as well as add labels. Boot volume and image verification will be covering in the later demos. For now, I will add an SSH key so that in the later demos, we will see how to connect to managed nodes using SSH. So in order to add an SSH key, you get multiple options to choose from. You can either generate an SSH key pair, you can paste your existing key, or you can upload a public key file which is in .pub format. In our case, let's go to the Cloud Shell and create an SSH key. So let me go to the Cloud Shell. Basically, in the future demos, we will see how to connect to the managed nodes in private and public subnets using SSH. Which is why I am creating my SSH key pair in the Cloud Shell machine. So let me first go to the default SSH directory in my home directory. Let me maximize the Cloud Shell for better viewing. Let me also clear the screen. Let me go ahead and generate an SSH key pair, for which I'll be using the command ssh-keygen. Let's hit enter. It says enter file in which to save the key. Let me use the default file name. Just hit enter here. It's asking to enter a passphrase. Let me hit enter. I'll leave it blank. Let's hit enter again. As you can notice, it has generated an SSH public private key pair for us. Let me do an ls command over here and see we have the id_rsa, which is our private key, as well as id_rsa.pub, which is our public key. Let me clear the screen. Now let me open up. Now let me copy the content of public key first. So for which I'll use the cat command. And this is my public key. So I'll select the public key and just copy it and minimize the Cloud Shell here. And let's select paste a public key option and paste our SSH public key in this box. So the public key that I pasted here will get installed on all the worker nodes in the cluster. You can also set labels for your worker node. This is an optional thing. Basically, setting a label can help you targeting of workloads at a specific node pool. Let's go ahead and click on next. On this page, we can review all the details that we have entered for the new cluster, including the name, the cluster type, the cluster version, as well as the network details and node pool details. Now remember, if you have not selected any of the enhanced cluster features, and if you want to create the new cluster as a basic cluster rather than the enhanced cluster, we can choose to create it as a basic cluster by checking this box over here. For this demo, I'll be creating a basic cluster. So I've checked the basic cluster over here. And if you notice in the review details section, you get to see that the cluster type has changed to basic. Once we review all the details, we can click on create cluster over here. Let me click on create cluster. And as you can see, the new network resources are now getting created for this cluster, which includes VCN, internet gateways, route tables, security lists, subnets, and after which it creates the cluster and the node pools for that cluster. So let me close this window. Initially, the new cluster appears in the console with a status of creating, as you can see over here. And once the cluster is created, it has a status of active and this turns green. So let's wait till it turns green. You can also check the status of your cluster creation by clicking on the work request in the resources section. And here you get to see the status of your cluster creation. As you can see, the cluster create is in progress and the node pool create has been accepted. So first the cluster gets created and then the node pool gets created and gets attached to the cluster. Well, as you can notice, the cluster is now active, but just to be sure that the node pool is created and attached to this cluster, we'll go back to the work request and see if the node pool create is succeeded. But as you can see, it's still in progress, which means our node pools are yet to be attached to this cluster. So let me click on the node pool create operation. And from the configuration, as you know, we have selected 3 nodes to be created in this node pool. It is launching those compute instances for us. Well, as you can see, the node pool create work request has completed successfully and our node pool has been attached to the cluster. So let me go back to the cluster details page and click on the work request. As you can see, the node pool create operation has been completed and it has ended successfully. From the breadcrumb menu, let me select clusters. As you can see, the OKE public demo 1 cluster is now active and available with one node pool having 3 nodes, running the Kubernetes version 1.27.2. Well, that's it from this demo where we saw how to create a Kubernetes cluster using the quick create workflow. So thank you for watching and see you in the next demo. Hello and welcome to this demo on Create Cluster with explicitly defined settings in the custom create workflow and attach managed nodes to the cluster. In this demo, we'll be creating a cluster using the Flannel CNI plugin. The Kubernetes API endpoint and the load balancers will be accessible directly from the internet, while the worker nodes will remain within the VCN in a private subnet. Initially, we will be setting up all the required networking resources like VCN, internet gateway, route tables, security list, and then we will proceed with creating the cluster using the custom create workflow. Creating Bastion and Bastion resources is not covered in this demo. In the upcoming lessons, we have covered Bastion and Bastion resources in much detail, so stay tuned for that. For now, let's get started. We have an official documentation that provides detailed information about the setup that I just mentioned. It provides you all the information about the networking resources that you must configure to create a cluster using custom create workflow. I'll be referring all the instructions provided in this documentation to set up all the required resources to create our Kubernetes cluster. I'll now head back to my OCI console. First thing, from the home page, I will navigate to VCN service. Click on networking. Under networking, we have virtual cloud network. I'll click on virtual cloud network. First up, I'll create a VCN. Let me fill up the details to create this VCN. The CIDR block that I'll be using is /16. We must make sure that the DNS resolution is checked. Next, I'll click on create VCN. Now my VCN is available. I'll go on and create all the other required resources. First up, I'll create Internet Gateway. I'll click on create Internet Gateway. Provide it a suitable name as per the documentation. I'll click on create Internet Gateway. Well, the Internet Gateway is now available. Next, I'll create NAT Gateway. I'll select NAT Gateway from the resources section. Click on create NAT Gateway. Give it a name. Leave everything to default. Click on create NAT Gateway. Next is service gateways. Click on create service gateway. Give it a suitable name. Under the services label, I'll be selecting all PHX service in Oracle Services Network. I'll go ahead and click on create service gateway. I'll close this window. Now I'll create route tables for our subnets. I know we have not created subnets yet, but let me create all the resources that would be required to create the subnets. I'll click on route tables and click on create route table. I'll be giving it a name as defined in the documentation. This is the route table for Kubernetes API endpoint. I'll select add route rule. Under the target type, I'll select Internet Gateway. And in the destination CIDR block, I'll provide open access, that is 0.0.0/0. And within the target Internet Gateway, I'll select my Internet Gateway that I recently created. Let's click on create. Next, I'll create route table for our private worker node subnet. I'll click on add another route rule. And for the private worker node subnets, we'll have to add two rules. One is the rule for traffic to internet. Let me select the target type as NAT gateway and destination CIDR block as 0.0.0/0. And target NAT, I'll select the NAT gateway that we created. I'll click on add another route rule. And here I'll add a rule for traffic to OCI services. Under the target type, I'll select service gateway. Under the destination service, I'll select all PHX service in Oracle Services Network. Under the target service gateway, I'll select service gateway name that we just created. Next, I'll click on create. Now we are left with creating one more route table, that is for our public load balancer subnet. I'll click on create route table again and give it a name. I'll add a route rule for Internet Gateway. Select target type as Internet Gateway. Under destination CIDR, I'll add 0.0.0/0 and select the Internet Gateway. Let's click on create. With this, we've created three route tables for our three subnets. One is for the service load balancer, the other one is for the private worker nodes, and the third one is for the Kubernetes API endpoint subnet, which is a public subnet. Next, we'll create security list for our subnets. I'll click on security list under resources tab and click on create security list. Firstly, I'll create a security list for our Kubernetes API endpoint. I'll add a name to it as per the documentation. For now, I'll create an empty security list with no rules for our Kubernetes API endpoint. Once we create the subnets, I'll come back and we will fill up the rules for both egress and ingress. Now, I'll add another security list for our private worker nodes. Similar to the previous security list, I'll leave this empty. I'll create another security list for our load balancer subnet and leave it empty for now. Alright, so we have created all the networking resources. Now the only thing that's left is to create subnets for our Kubernetes API endpoint, worker nodes, and load balancer. I'll proceed to create subnets for these resources. Let's click on create subnet. Give this subnet a name. The first subnet that I'm creating is for the Kubernetes API endpoint. I'll give it a name Kubernetes API endpoint. The subnet type is regional, which is recommended. I'll provide a CIDR block with /30 CIDR notation. As for the Kubernetes API endpoint, having a bank of 4 IP addresses is sufficient. Under the route table section, I'll select the route table we created for Kubernetes API endpoint. Under the subnet access, we'll be going with public subnet for the Kubernetes API endpoint. As you can notice, it is checked already. We must ensure that the DNS resolution is checked, which is checked already. Under DHCP options, we'll go for the default DHCP options for this VCN. And under security list, let's select the security list that we just created, which is seclist-Kubernetes API endpoint. Next, I'll click on create subnet. Well, the subnet is in provisioning state and we'll have to wait till it gets active. In the meanwhile, I'll create subnets for our private worker nodes and public load balancer. Subnet type is regional, which is recommended again. And for the CIDR block field, let me provide a suitable CIDR block. /24 notation allows you 256 IP addresses, which is sufficient for this demo. You can always change the CIDR notation to meet your requirements. Under the route table, let me select the route table we created for worker nodes, which is route table-worker nodes. And this time, the subnet access is private subnet for our worker node. I'll select private subnet. Leave the DNS resolution as checked. Under DHCP options, we'll opt for default DHCP options. Under security list, let me select the security list we created for worker nodes, which is seclist worker nodes. Next, I'll click on create subnet. Now I'll click on create subnet to create subnet for our load balancer. Under CIDR block, I'll use 10.0.2.0/24, which provides me with 256 IP addresses. Under route table, I'll select the route table we created for service load balancers. And like I mentioned, the load balancer will be part of public subnet accessible via the internet, which means we'll have to select the public subnet. That is the default selection. Under DNS resolution, I'll leave the option as checked. And under DHCP options, we must select the default DHCP options for the VCN. Under security list, I'll be selecting the security list we created for load balancer, which is seclist-load balancers. And let's click on create subnet. Now that we have created subnets for our load balancer, worker nodes, and Kubernetes API endpoint, What's left is to add rules within the security list that we have associated to each of these subnets. Since this video is getting a bit too long, let me pause here and we will continue in the next video. I hope you're enjoying the demo so far. See you in the next part. Welcome back. Let's continue from where we left off in our last demo. Now that we have created subnets for our load balancer, worker nodes, and Kubernetes API endpoint, what's left is to add rules within the security list that we have associated to each of these subnets. Let's go to the security list. First up, I'll set rules for the Kubernetes API endpoint. I'll select the security list for Kubernetes API endpoint. Currently, there are no ingress and egress rules set up in the security list for Kubernetes API endpoint. I'll refer the official documentation and set up the rules as given in the official documentation for each of the security list associated to our different subnets. As you can see on the screen, these are the list of ingress rules and egress rules that we must add for the security list that we have associated to our public Kubernetes API endpoint subnet. Similarly, we have a bunch of ingress rules and egress rules for security list rules for the private worker node subnet and one for the load balancer. In the interest of time, in this demo, I'll show you how to set up ingress and egress rule for the public Kubernetes API endpoint security list. And for the rest of the security list for our Kubernetes worker nodes and the Kubernetes load balancer, I'll pause the video and resume once I've created those rules. Let's transition back to our OCI console. And let me start by adding ingress rules. To add ingress rule, I'll click on Add Ingress Rule button over here. The first rule is to allow communication from Kubernetes worker nodes to Kubernetes API endpoint, for which the source CIDR is the CIDR of our worker nodes. And the destination port is 6443. The protocol selected is TCP. I'll also add the description. Now I'll click on Add Ingress Rule to set up the next rule, which is again for worker nodes to control plane communication. The source CIDR is the CIDR of our worker nodes. The protocol is TCP and the port is 12250. I'll add the description from the documentation. I'll proceed to add another rule. This rule is for path discovery from worker nodes to Kubernetes API endpoint. And since this is the rule for path discovery, the protocol will change to ICMP. The type is set to 3 and the code is 5. Let me add another ingress rule to allow access to the Kubernetes API endpoint from the internet. The source CIDR this time is 0.0.0/0. The IP protocol remains TCP and the destination port here is 6443 as the Kubernetes API endpoint listens on port 6443. Next, I'll click on Add Ingress Rules to add these 4 rules to the security list. And as you can notice, the 4 rules have been added to our ingress rules. To add egress rules, I'll select egress rules from the resources section. Click on Add Egress Rules. And these are the set of egress rules that I'll be adding to the security list. For the first rule, I'll be selecting the destination type as service. Under destination service, I'll select all PHX service in Oracle Service Network. Under IP protocol, we'll be using the TCP protocol. The destination port range remains open. I'll add a suitable description for this rule. This allows Kubernetes control plane to communicate with the cluster. I'll select Add Another Egress Rule. For the second rule, I'll select the destination type as service, destination service as all PHX service. This time the IP protocol is ICMP and the type is 3, code is 4. The purpose is for path discovery. I'll add the third rule from the list, which is to allow Kubernetes control plane to communicate with worker nodes, which means I'll have to provide the destination CIDR of a worker node, that is 10.0.1.0/24. Protocol is TCP and the destination port range is all. And the final rule is again for path discovery from Kubernetes API endpoint to the worker nodes, which means I'll provide the CIDR for our worker nodes. Protocol has to change to ICMP. The type is 3 and the code is 4. The purpose is path discovery. Next, I'll click on add egress rules. And this is how we have added the 4 rules as specified in the official documentation. Now, in the interest of time, I'll pause the video here and come back when I've filled up the security rules as defined in the documentation for our load balancer subnet as well as the worker node subnet. Well, I have populated all the security list rules as defined in the official documentation for the remaining security list, that was for load balancers and worker nodes. I'll quickly show it to you. I'll select the security list for worker nodes first. And these are the set of ingress rules and the egress rules that I've defined in it as per the documentation. Let's head back. And this one's for the load balancer, where I've added ingress rules to allow traffic on port 443 and 80. Now, adding an ingress rule for the load balancer completely depends on application. You can either go for an internet CIDR or go for a specific CIDR here. And again, the protocol and the port that you open up is application specific. And you can customize as required. But for the egress rules, you must define these rules where you're allowing communication with the worker node ports as well as with the kube proxy on the worker node. Since this video is getting a bit too long, let me pause here and we will continue in the next video. I hope you're enjoying the demo so far. See you in the next part. Welcome back. Let's continue from where we left off in our last demo. Now that we have created all the network resources required to set up a Kubernetes cluster, I'll go to the Kubernetes service page from the developer service. Click on Kubernetes cluster. And I'll be creating a cluster using the custom create workflow. I'll select custom create option and click on submit. Now in the create cluster page, let me provide a suitable name for our cluster. The compartment where I'll create my cluster is CTD OKE and the Kubernetes version is the latest version from the list. Under advanced options, we have multiple features as well as options available that you can enable for your custom cluster. But I won't be talking about them in this demo as we have separate dedicated lessons for each of these features. Let me click on hide advanced option and let's click on next. Now we are on the network setup page where we will be specifying the existing network resources to use for the new cluster. Under the network type, I'll be selecting Flannel overlay. And let's select the VCN that we created for this cluster. From the drop down, let me select the VCN which was Acme Dev VCN. Let's select the subnet for Kubernetes Service Load Balancer subnet, which is our load balancer regional subnet. Let's select the Kubernetes API endpoint subnet, which is again a regional subnet we created for our Kubernetes API endpoint. Since we have not defined any security rules in the network security group, I'll leave this option unchecked. But I'll check this option as I want a public IP address to be assigned to our cluster, which will make our Kubernetes API endpoint accessible from the internet. Under Show Advanced Options, you can provide CIDR blocks for your Kubernetes service as well as pod CIDRs. This is basically a group of network address that can be exposed as Kubernetes services cluster IP and should be expressed as a single contiguous IPv4 CIDR block. And remember, the CIDR block you specify over here must not overlap with the CIDR block for the VCN. Similarly, pod CIDR block is the available group of network addresses that can be allocated to pods running within the cluster and must be expressed as a single contiguous IPv4 CIDR block. Again, remember, the CIDR block that you specify here must not overlap with the CIDR blocks for the subnets in the VCN and can be outside the VCN CIDR block. And as these are optionals, I'll leave them as blank. I'll click on Next. Here, I'll have to specify the configuration details for our first node pool that we'll be attaching to our cluster. The pool name is pool 1. The compartment where I'll create all the required resources is CTD OKE. The version that you select here will be the version of Kubernetes that will run on each of the worker nodes in the node pool. I'll leave it as default. Now under the node placement configuration, we must select an availability domain in which to place the worker nodes. Let me select one of the options. Let me select the worker node subnet which we created earlier. Selecting fault domains is optional. I'll leave it as blank. Under the Show Advanced options, you get to select the capacity type. You can choose from on-demand capacity, capacity reservation, and preemptible capacity for the worker nodes that will be running on your cluster. I'll leave it to default, which is on-demand capacity. And we can optionally add another row to select additional domains and subnets in which to place the worker nodes. For now, I'll stick to only one entry. Now under the shape and image section, we can select the node shape, that is the shape using which our worker nodes will be created. I'll leave it as the default one, that is VM standard E3 Flex. And for the image that you want to run on the worker nodes, you can change the image if you wish to. I'll leave it as default. Under the node pool options, we can specify the number of worker nodes to add in the node pool. By default, the value is 3. We can scale it up or scale it down. I'll leave it to the default value. Under the boot volumes, you can configure size and encryption options for the managed node boot volumes. I'll leave it to the default settings. Under the Show Advanced options, you can specify the cordon and drain settings for your worker nodes. And optionally, you can provide an initialization script. It's basically a script for Cloud Init to run on each instance hosting managed nodes when the instance boots up for the first time. Remember, the script that you specify must be written in one of the formats supported by Cloud Init, for example, cloud-config, and must be supported file type, for example, .yaml file. You can either choose the Cloud Init script file or you can paste the content of Cloud Init script over here. By default, the managed nodes added to this managed node pool will automatically get the following Kubernetes label applied, that is name and pool 1. If you want to add a different label, you can always click on add another row and provide a different key value pair. You can add node pool tags. Again, this helps you add your own metadata. You can also add tags to the worker nodes in your node pool. And finally, you can add an SSH key if you want to access your worker nodes within the cluster. I'll be adding a public key. Let me add a public key from the SSH key pair that I have. I'll click on Next to review the cluster details that we have entered for the new cluster. This is the review page where we can cross-check all the details. Now, since we have not used any of the features of an enhanced cluster like virtual nodes or any of the add-ons, it's still allowing us an option to create this cluster as a basic cluster. you want to create a cluster as a basic cluster, you must check this option and the type of the cluster will change to basic. But if you want your cluster to be an enhanced type cluster, then you must unselect this and the type of the cluster will be set to enhanced. All right, I have reviewed all the information like the VCN name, service, load balancer subnet, Kubernetes API endpoint subnet, as well as the node pools information where we have created a managed node pool with one node pool in it, having 3 worker nodes. And the shape we have selected for the worker nodes is VM standard E3 Flex with Oracle Linux 8 operating system. And the network type is set to Flannel overlay. I'll click on create cluster to create the new cluster now. Let me close this window. Well, it will take some time before the cluster status changes to active. Currently, the cluster is in creating state. You can also check the work request to see what is the progress with cluster creation. Currently, the cluster creation stage is in progress. Once it's active, we'll see that the node pool creation stage will be in progress. And once the node pool is created, it will be attached to the cluster. Let's wait until we have a green signal on these operations and our cluster status changes to active. Well, after a while, our cluster is now active and ready to use. Now to access the cluster and create resources within it, we will select the Access Cluster button. You get 2 options to choose from, either go for Cloud Shell access or go for local access. In our upcoming lessons, we have covered the topic Access Your Cluster in more detail. For now, I'll select Cloud Shell access and click on Launch Cloud Shell. We must configure the kubeconfig file to enable the kubectl command line utility to access our cluster. Let me copy this command. Our Cloud Shell machine comes pre-shipped with kubectl command line utility. Let me go ahead and paste the command I just copied and hit enter. Well, the kubeconfig file has been configured. Now I'll check whether I'm able to connect to the Kubernetes cluster and retrieve the nodes running within the cluster, for which I'll run the command kubectl get nodes. There you go. We have retrieved the list of 3 nodes that are running on our cluster. And just to cross check, I'll go to the node pools and click on node pool 1 and just cross check the IPs that were retrieved. And as you can notice, the IPs for our worker nodes are matching with the one that we retrieved using the kubectl, which means we are connected to the cluster now. And I'll now demonstrate how to create deployment on this cluster, which will create 3 pods running Nginx image. And the command is kubectl create deployment, name of my deployment, image to be used within the pods, and the number of pods are set to 3. I'll hit enter here. Well, it says deployment created. Let me check the status of the deployment. As you can notice, it says 3 out of 3 pods are up and running. I'll also show you the pod status using kubectl command. And these are the 3 pods that are running within my worker nodes for the deployment Mahindra-deployment. Now I'll go ahead and expose the deployment using a load balancer service using the kubectl expose command. I'll hit enter on this command. And as it says, the service lb-service has been exposed. Let's check the service details using kubectl command. Well, from the list, we can notice that the service lb-service of type load balancer is created and the external IP is still in pending state. We'll have to wait until a load balancer is created and it's assigned a public IP address. Let's rerun the kubectl get service command and see if we have the external IP available now. Well, there you go. We have the external IP available. I'll copy this IP and paste it on a new tab. And there you go. Our Nginx web server is now accessible using the load balancer service. With this, we come to the end of this demo where we successfully created a Kubernetes cluster using the explicitly defined settings and network resources in the custom create workflow. I hope you enjoyed all the demos in this series. See you in the next one. Thank you for watching. Congratulations on making to this module of our course, Setting up OKE Cluster Access. Your progress in this course showcases your commitment towards mastering OCI Container Engine for Kubernetes, and I am thrilled to guide you further. In this module, we'll cover how to enable access to your Kubernetes cluster for easier management and interactivity. In this module, we'll cover how to set up Cloud Shell access as well as local access to your Kubernetes cluster and interact with them using the kubectl utility. Additionally, we'll cover how to manage an SSH connection with your managed nodes as well as set up a bastion service in order to connect to your Kubernetes workloads in a secure fashion. So let's dive in. Hello and welcome to this lesson on accessing a cluster using kubectl. I am Mahendra Mehra and I am your senior OCI instructor at Oracle University. Alright, let's dive into the practical side of things. When it comes to managing a cluster created with Container Engine for Kubernetes, we've got a handy tool in our toolkit, that's kubectl. Now, you can either roll with the kubectl installation that comes with Cloud Shell or opt for a local installation, it's your call. But here's the deal. Before you start welding kubectl like a pro, you need to tell it which cluster it should be bossing around. And how do you do that? By setting up the cluster's kubeconfig file. The kubeconfig file, by default named config, is stored in the user's home directory under the .kube directory, and it provides the necessary details to access the cluster. This little file is your ticket to making operations on your cluster seamless and precise. Let's understand the kubeconfig file in more detail. Firstly, a kubeconfig file is your gateway to multiple clusters, which is neatly organized as different contexts. The current context element in the kubeconfig file is your guide specifying the cluster where all the actions happen. Now, here's a neat trick up its sleeve. A kubeconfig file includes an OCI command. This command works behind the scenes, dynamically generating an authentication token and seamlessly inserting it whenever you fire up a kubectl command. But here's the catch. The authentication tokens are short-lived, specific to the cluster, and tailored for individual users. In other words, you can't pass around kubeconfig file like party invitations. Each user needs their own kubeconfig file to access Kubernetes cluster, and this file cannot be shared between users. Alright, let's fine-tune our Oracle Cloud Infrastructure command in the kubeconfig file. Here's the scoop. The command in the kubeconfig file plays nice with your current CLI profile. Now, if you are the type who likes to keep things interesting with multiple profiles across different tenancies in your CLI configuration file, we've got a trick for you. Specify which profile to tap into when generating the authentication token. How? Easy. Just use the following format profile-name in the command. And yes, profile-name is the actual name of the profile you've defined in your CLI configuration file. So replace this placeholder with the actual name that you have defined in your CLI configuration file. Set the OCI CLI profile environment variable before you unleash your kubectl commands. It's as easy as this. Execute the command export OCI underscore CLI underscore profile and set it to your profile name. Remember, profile-name is the specific name of the profile you've laid out in your CLI configuration file. Once done, verify that the kubectl can connect to the cluster using the kubectl get nodes command, and this should return the list of nodes available in your Kubernetes cluster. The authentication tokens generated by the OCI CLI command in the kubeconfig file are tailor-made for individual users using kubectl. However, if you are thinking bigger, like having other processes and tools, say your CI/CD tools accessing the cluster, that's a different ballgame. And in such cases, it's time to consider creating a Kubernetes service account and slipping its authentication token into the kubeconfig file. Watch out for IAM policies throwing in a twist. If there's a policy playing gatekeeper, allowing access only to users with golden touch of multi-factor authentication, we've got your back. Adding a touch of magic to your kubeconfig file with the --profile, profile name, --auth, and security token. Simply drop these into the argument section of the kubeconfig file, ensuring the MFA verified user's profile is specified. Remember, the profile-name is the name of the MFA verified user's profile defined in the Oracle Cloud Infrastructure CLI configuration file. Streamline your process with the OCI CLI profile environment variable. Before unleashing your kubectl commands, set it to the name of the MFA verified user's profile defined in the CLI configuration file. Just execute export OCI underscore CLI profile, specify the profile name, and you are good to go. After you've sprinkled these updates into your kubeconfig file, make sure the user attempting to access the Kubernetes cluster is MFA verified. Attempting otherwise might just get you a stern unauthorized message, so keep those MFA verified keys handy. You must verify that the kubectl can connect to the cluster using the kubectl get nodes command, and this will result in the list of nodes that the cluster is operating with. To wrap up, in this lesson, we laid the foundation by exploring the essential kubeconfig file for accessing our cluster. In our next lesson, we are diving into the practical side, covering two powerful ways, Cloud Shell access and local shell access, to seamlessly connect with our clusters using kubectl. See you in the next video. Thank you so much for watching. Welcome back. In this lesson, we are diving into the practical side of accessing our clusters using kubectl. We'll explore two powerful methods, Cloud Shell and local shell access. So without further ado, let's jump right in. Let's walk through the steps of setting up Cloud Shell access to your clusters. Here's what you need to know. First things first, when your cluster's Kubernetes API endpoint boasts a public IP address, you can smoothly access it in Cloud Shell by configuring a kubeconfig file. You must navigate to the OKE console and click on the Access Cluster button. A helpful Access Your Cluster dialog box will pop up, providing you with the precise command to establish a connection with your cluster. Pay attention to the details. If you have already got a kubeconfig file hanging out in the location you specify, fear not. The information about your cluster will gracefully append as a new context to the existing kubeconfig file. The current context element will elegantly point to this fresh addition. Now, if you decide to get creative and save your kubeconfig file somewhere other than the default location or with a different name, just set the kubeconfig environment variable to steer kubectl in the right direction. You can do so by setting the kubeconfig variable to the path where your kubeconfig file resides. Final check. Let's ensure everything is in order. Execute the kubectl get nodes command in the Cloud Shell. If all is well, you will be greeted with valuable information about the nodes in your cluster. Let's look at setting up local access to the cluster. Picture this. Your cluster's Kubernetes API endpoint lacks a public IP address. No worries, you can still access it from your local terminal as long as your network is paired with the cluster's VCN. Now let's talk security. The first thing is to generate an API signing key pair and upload the public key in the OCI user console. It's like giving your local access a VIP pass. Time to bring in the big guns. Install and configure the Oracle Cloud Infrastructure CLI. This is your backstage pass to seamless cluster interaction. Step 4 is to set up the kubeconfig file. Let's discuss this step in more detail. First things first, make sure you've got the kubectl installed. And here's a tip. Ensure your kubectl version aligns closely with the Kubernetes version running on the control plane nodes. Create a cozy spot for your kubeconfig file. The default expectation is .kube directory within your home directory. Use the Oracle Cloud Infrastructure CLI command to set up the kubeconfig file, ensuring it's saved in a location that kubectl can easily reach. If you plan on saving your kubeconfig file somewhere else, no worries, just tell kubectl where to find it by setting the kubeconfig variable to the location where you have kept your kubeconfig file. Lastly, let's do a quick check. Run the kubectl space version command. What it does is it tells you the version of kubectl you have installed locally, the Kubernetes version on the control plane nodes, and a little extra. Run the kubectl get nodes for a snapshot of the nodes in your cluster. With these two commands, you can verify that the cluster access has been set up successfully. To conclude, in this lesson, we demystified the process of configuring cluster access using both Cloud Shell and the trusty local terminal. Now you have the tools to seamlessly connect and manage your clusters. I hope you found this lesson helpful. See you in the next lesson. Thank you so much for watching. Hello and welcome to this demo on setting up Cloud Shell access to OKE clusters. Let's get started. If you recollect from the previous demo, OKE-public-demo-1 is the cluster that we created whose Kubernetes API endpoint was in a regional public subnet, as well as the worker nodes were hosted in a public subnet. When a cluster's Kubernetes API public endpoint has a public IP address, you can access the cluster in Cloud Shell by setting up a kubeconfig file. To set up a kubeconfig file, click on the Access Cluster button. This displays the Access Your Cluster dialog box, and you get to choose from two options. One is the Cloud Shell access, and the other one is a local access. For this demo, we'll continue with Cloud Shell access. Under Cloud Shell access, you have to perform two steps. One is to launch the Cloud Shell. So let me click on this Launch Cloud Shell button. And the second step is to copy this command and paste it in the Cloud Shell. Let me copy this command and paste it over here and hit enter. Well, as you can see, a new config has been returned to the kubeconfig file hosted in the location my home directory under the .cube directory with the name config. Also make a note that the cluster ID, which is the cluster OCID over here, is the OCID of the cluster that we are trying to connect to. So let me close this window, and if you notice, the cluster OCID given over here as well as the cluster OCID given in the command is matching. So now that the new configuration has been written in the kubeconfig file, the current context is currently pointing to the cluster named OKE public demo 1. Now the next step is to verify that kubectl can access the cluster. Kubectl, like I mentioned in the earlier demos, is a command line utility that lets you interact with your Kubernetes cluster. Let me run the kubectl get node commands to interact with my OKE public demo 1 cluster. Well, as you can notice, it returns me the information about the nodes in the cluster. My cluster is a 3 nodes cluster, basically one node pool running 3 nodes in it. To cross-check this information, let me go to the console and let me click on the node pools in the resources section. Let's click on pool 1 and let me scroll down. And if you notice, the private IP of my worker nodes in the console matches to the one that we see as the output of our command kubectl get nodes. Now we can use kubectl to perform other operations and create Kubernetes resources on the cluster. Let me clear the screen. Let me go ahead and use an inline configuration to create a deployment resource in the Kubernetes cluster. Alright, so I created a deployment named Mahindra-deployment, which is running an Nginx latest image with 3 pods in it. Let me also check the pod status. So run the kubectl get pods command to check the pod status. And as you can see, all the 3 pods are in the running state. Well, that's it from this demo where we saw how to access an OKE cluster using the Cloud Shell access to the cluster. I hope you enjoyed this demo. See you in the next one. Thank you for watching. Hello and welcome to this demo on setting up local access to OKE cluster. So let's get started. If you recollect from the previous lesson, these are the steps that we need to configure in order to set up a local access to our clusters. Just to give you a short overview, we will first create an API signing key pair. We will upload the public key of the API signing key pair in our user tenancy. And then we will install and configure OCI CLI. We will also set up kubeconfig file in our local machine. Also ensure that kubectl is installed and later verify that kubectl can access the cluster. So let's get started. I've logged in into my OCI console and let's go to the Kubernetes cluster service page. OKE public demo 1 is the cluster which we will be setting up access to from the local terminal. Let me click on the cluster. Just to recollect, our Kubernetes API endpoint is placed in a public subnet, whereas the worker nodes are placed in a private subnet. In this demo, we will be setting up our local terminal to access the Kubernetes API endpoint that has a public IP address. To access a cluster with a private Kubernetes API endpoint from a local terminal, we must configure a bastion using OCI bastion service, which we will be covering in the later demos. Let me open up my local terminal. This is my local terminal, which is running on an Oracle Linux 8 operating system. First thing that I'll be doing here is I'll be configuring the OCI CLI. Now we know that step 1 and step 2 involve creating RSA key pair and then uploading the public key. But we will be doing step 1, 2, 3 all together. Let me first install OCI CLI on this machine. To check whether OCI CLI is already configured, you can always run an OCI space -v command. And since OCI CLI is not installed, first step that I'll be doing is to install the OCI CLI, for which I'll be using the command sudo dnf -y install and the package name, which is Oracle Linux Developer Release EL8. Let me go ahead and hit enter. Remember, I'm using Oracle Linux 8 operating system on my local terminal. In case you're using another operating system like Windows, Mac OS X, or any Linux or Unix variant, you must refer the official documentation and see what are the commands and steps to install OCI CLI. Let me hit enter. Well, from the output, it seems that the package Oracle Linux Developer Release EL8 is already up to date. Let me go ahead and install the OCI CLI. The command is sudo dnf install python 36-oci-cli. Let me hit enter. Well, it's asking me to go ahead with the installation. Let me say yes and hit enter. And it's installing the OCI CLI on my local machine. Well, the installation is complete. Let me check if the OCI CLI is installed. Let us run the OCI-v command. As you can see, the OCI CLI version 3.2 is installed on my machine. Let me clear the screen. And like I mentioned, you can refer the official documentation, which is this. And this is a quick start guide that lets you quickly install and configure OCI CLI on different environments like Oracle Linux machines or Mac OS, Windows, Linux, and Unix environments. You can search within the Oracle documentation by going to the docs.oracle.com website. And there you just simply have to search for installing the CLI, or you can search for OCI CLI and it will guide you to this particular page. Let's head back to our local terminal. Now that we have installed the OCI CLI, the next step is to configure it. The command to configure OCI CLI is OCI setup config. Let me run the OCI setup config command to configure the OCI CLI. Let's hit enter. Now it's asking me to enter a location for the config file. I'll use the default location and I'll hit enter. Now the next thing that it is asking me for is the user OSIT. Let's go to our OCI console and copy the user OSIT and paste it over here. In order to find your user OSIT, you have to click on the profile menu, go to my profile. Under your profile information page, simply copy the OSIT. Let me copy my OSIT and let's head back to the local terminal. Let me paste the OSIT here. Let's hit enter. Now it's asking to enter tenancy OSIT. Let's head back to the console and copy the tenancy OSIT. You can find the tenancy OSIT in your profile page. Go to your tenancy. This opens up the tenancy details page. And from the tenancy information tab, you can simply click on copy OSIT and let's go back to the local terminal and paste it here. Let's hit enter. Now it's asking to select a region, right? In my case, the region is US Phoenix 1. Let me provide the index for my region, which is 50. Let me reconfirm the region that I'm working in is US West Phoenix and 50 is the index for US Phoenix. All right, let's hit enter. In the next step, it is asking whether I wish to generate a new API signing RSA key pair. In my case, the local terminal does not has a API signing RSA key pair. So I'll go ahead with this option. Let me enter Y. Now it's asking a directory for the keys to be created. Let it be the default directory, which is .oci directory under my home directory. Let me hit enter. And it's asking for the name. Let me go with the default value, which is OCI underscore API underscore key. Let me hit enter. Again, it's asking for a passphrase for the private key. Let me keep it blank. I'll hit enter here. And there you go. My OCI CLI has been configured. Now the next thing is I'll have to copy the API signing RSA key pairs public key information and I'll have to add it as an API key in my user account on the OCI console. In your case, if you already have an API signing key pair that you wish to reuse, simply copy the public key information and paste it in the API keys within your user settings on the OCI console. So let me copy the public key information. As you saw that the API signing key pairs were created in the .oci directory. Let's head to the .oci directory. Let me clear the screen first. Let's go to the .oci directory. Let me do an ls over here. And as you can notice, we have the two keys, which is OCI underscore API underscore key dot pem. This is our private key. And OCI underscore API underscore key underscore public dot pem, which is the public key. Now let me copy the content of the public key and paste it in the API keys section on my user console. So let's do a cat OCI API underscore key underscore public. And let's copy this entire information. Let's head back to our OCI console. Now let's select my profile, and under the API keys in the resources section, let's click on add API key. And from the options, let's choose the paste a public key option. Let me paste my public key over here. And let's click on add. Once we click on add, it gives us the configuration file preview. This is how our OCI CLI configuration would look. And let's click on close. Let's head back to our local terminal and let's check the configuration file in our local terminal. Let me do an ls over here. So this is the configuration file. Let me open it up for you. If you notice, the user OSID, the fingerprint for our API key, also the API key fingerprint matches with the one that we just uploaded in the OCI console. And then information like the location of our private key, the tenancy OSID, and the region identifier. Let me clear the screen. Now to check whether the OCI CLI is configured properly or not, we will run OCI commands to check if we can access OCI resources. Let me run an OCI os ns get command. As you can see, it has returned me my Oracle Cloud account information, which is int Oracle Rohit. This confirms that my OCI CLI is configured correctly. Let me clear the screen. Now, since this demo is getting a little long, I will pause here and we will continue in the next demo. I hope you found this demo interesting so far. See you in the next part. Hello and welcome. Let's continue where we left off in our previous demo. So let's get started. Now the next step is to install kubectl. kubectl is a command line utility that helps us interact with our Kubernetes cluster. In our previous demo where we used Cloud Shell to access Kubernetes cluster, the kubectl utility comes pre-shipped with the Cloud Shell machine. In this case, the kubectl is not installed on my local machine. We can confirm that by running the kubectl command. It says kubectl command not found. Let's go ahead and first install kubectl packages. I'm referring this documentation over here to install and set up kubectl. In my case, it's a Linux terminal, so I'll select Linux and let's copy the curl command to download the latest release. Let me head back to my local terminal and paste the curl command. Let's hit enter. All right, so the package has been downloaded. Let me do an ls. Confirm if the kubectl package has been downloaded. Next thing is to make the kubectl binary executable. Let's run the chmod command. Let's hit enter. And finally, we must move the binary into your path variable, which is usr local bin kubectl. Let me copy this command. Paste it here. All right, so our kubectl has been installed and configured. Let me run a kubectl command again. And as you can see, it gives me all the options, which means kubectl has been configured correctly. Let me clear the screen. Just to check the kubectl version installed on my local terminal, let me run the kubectl version command. And the version that it's running is 1.28.4. Let me clear the screen. All right, so now that we have configured OCI CLI, installed kubectl, and also copied the public API signing key pair to our OCI console, the next thing that I'll be doing is now setting up the kubeconfig file. So let's go back to our OCI console. Let me go to the Kubernetes cluster page. click on developer service. Let's go to Kubernetes cluster. Let's click on the cluster from the cluster list page. Let me click on access cluster this time. And this time around, we'll be using the local access. So let me click on local access. And let's follow all the steps given here. By far, we have already downloaded and installed OCI CLI. We have configured it for use. And as the information says that the OCI CLI version must be 2.24.0 or later. And in our case, it's the later version. The next thing that we'll be doing is to create a directory to contain the kubeconfig file. Let me copy this command and let's head back to our local terminal. Let me paste that command over here. This creates a hidden kube directory in my home directory. Let's hit enter. Let me go to the home directory and let's do an ls. And as you can notice, we have this .kube directory created. Now the next command that I'll run is to access the kubeconfig file for our cluster via the VCN native public endpoint. Remember, our cluster's Kubernetes API endpoint is in a public subnet for which I'll be copying this command. Let's head back to our local terminal and paste the command here. Let's hit enter. And it says a new config has been returned to the kubeconfig file, which is available in the .kube directory that we just created. So let me go to the kube directory. Let me hit enter. And if I do an ls here, you can see that the config file is created. Let me open up the config file for you. As you can notice, it has all the information like the cluster OCID. The cluster OCID ends with DPQ. Let me head back to our OCI console. Let me close this. And just to confirm, our cluster OCID is ending with the letters DPQ. This is the cluster that we have created access to from our local terminal. Now that we have set up the access, the last step is to verify that the kubectl can access the cluster, for which I'll be running the kubectl get nodes command. Let me hit enter. And there you go. From the output, we can see that it has returned us the list of worker nodes. And this confirms that we were successful in setting up local access to our cluster Kubernetes API endpoint in the public subnet. Now let me run a command with inline configuration to create a deployment within the Kubernetes cluster. The command is kubectl create deployment. Let's give the deployment a name. This is Mahindra-Nginx. Let's provide the container image. Let's set the replicas for the pod to 2. Let's hit enter. And it says the deployment is created. Let's check whether the pods are in action. So let's do a kubectl get pods command. And there you go. We can confirm that the 2 pods as part of our deployments are in the running state and have been created successfully. Well, that's it from this demo where we saw how to set up local access to our cluster. I hope you enjoyed the demo. See you in the next one. Thank you so much for watching.